So let me thank Professor Ranjini Bandyopadhyay for this asking me to give these talks today and tomorrow. I'll be talking on thermotropic liquid crystals, basically. That's the field I have been working on for 6 decades or so now. And I think most of you may be familiar with the first few slides that I'm going to show in any case. See, these were discovered by a botanist called Reinitzer back in 1888. Shape anisotropy of organic molecules is essential for the formation of these thermotropic liquid crystals. Of course, organic compounds can be synthesized in any shape. The chemists are extremely clever. And a vast majority of mesogenic or liquid crystals, in fact, mesogenic also means those which form liquid crystals. These compounds, most of them have rod-like molecules with a length about 4 to 5 times longer than the width. So this is the cartoon picture that you always see, two-dimensional structure. The first one is a crystalline phase where you have, in this case, two-dimensional periodicity of the molecules. You heat it to some temperature and it melts. Merely because the molecules have the shape anisotropy, the liquid which forms has a spontaneous orientational order. This is the simplest liquid crystal, the nematic, which is also the most useful because that is what is used in all the displays that all of you are using practically day in and day out. This has to be heated to an even higher temperature for it to lose the orientational order and go to the isotropic phase. Of course, one of the features which is very special to this nematic phase, I'm going to contradict this tomorrow, at any rate, for most of the compounds, is that N is apolar. Even when the molecules are highly polar, this is what I'm going to contradict tomorrow. Very recent results. Fortunately, there is something interesting. So, for example, this is a very well-known room temperature nematic liquid crystal forming compounds. It has a cyanoine group which has 4.5 dBs, and another compound which has a side group which has the same highly polar group. Both of these exhibit nematic phase over a fairly large temperature range, and they have apolar order, both of them. How do we know that they have apolar order? It's very trivial. You take a drop of the liquid between a slide and cover slips, look at it in a polarizing microscope, then you see what these two dark brush defects between cross polarizers. So you see one there, you see one here. And these brushes can only be understood if the director field goes around that disclination point. This is a projection of the line in the field of view. In fact, these are line defects. These are the topological defects of the nematic phase. You can get these two brush defect only if there is no distinction between the left arrow and the right arrow. If there is a distinction, you cannot get it. It's again a good exercise for you to figure out why it is so. And this particular photograph has an additional feature. Here there is a thing with 6 brushes. See, the strength of the defect depends on the number of brushes that you see. These are called half-strength defects. Therefore, this has got a strength of 3/2. In fact, if you have a pure compound, the energy, the positive energy carried by a defect goes as the strength square. So in principle, this shouldn't exist. It exists only because it's a two-component system, and there is actually a gradient of the concentration from the disclination line outwards, which can stabilize it. This was some work which we did long ago. Anyway. So since you have an apolar order, the relevant order parameter is the second rank tensor. And the magnitude of the order parameter is defined like this. It's the statistical average of 3 cos squared theta minus 1/2. Whereas if it were a polar order, it would have been just cos theta average. Theta is the angle made by the long axis with the direct, which is the average orientation direction of the molecule. So the first question that you ask, in fact, I'm not going to go chronologically, I will come back to this question again tomorrow, is what is the molecular origin of this order? Of course, Ansager, in a seminal contribution in 1949, he developed the first correct theory to demonstrate that the hard-rod interactions between the rod-like molecules is good enough to give you the orientational order. In fact, there is a decrease in the orientational entropy, obviously. Due to the orientation, there is a decrease in that contribution to the entropy. But at the same time, as the molecules can move up and down freely, there is an increase in the translational entropy. In fact, the competition between these two leads to the isotropic to nematic transition. In fact, probably this is the very first time that the competition between two entropies was shown to be enough to have a phase transition liquid in any material for that matter. And of course, this means you have to press it. You have to bring the molecules closer. You have to apply pressure, which is not a convenient external influence. It is better to have temperature as your convenient external forcing. Then Mayer-Saupe in 1958 argued that anisotropic dispersion interactions between the molecules which have a rod shape is the real origin for the attractive interaction which leads to the orientational order. In fact, the Mayer-Saupe theory is perhaps one of the most highly cited papers in the field of liquid, maybe the most highly cited paper in the field of liquid crystals. So usually, in fact, I'll just go through this quickly. Any molecular mean field theory like this, you start by defining a single particle potential. Each molecule has this potential. U0 depends upon the chemistry of the system that you are studying. S is the orientational order that I defined. P2 cos theta I is the variable whose average is the orientational order. So once you have the single particle potential, you can write the normalized Boltzmann distribution. Once you have the distribution function, you know how to solve the problem. You can write the entropy, which is the statistical average of logarithm of f of theta, and the internal energy, which is, of course, the statistical average of u. So once you have these two, you have the free energy and you can calculate everything else. So that's the typical mean field theory that one uses in any field that you like in condensed matter. So this distribution function is sharply peaked near f theta equal to 0 and it goes down at pi by 2. And since the order is apolar, there is a mirror symmetry around pi by 2, which means there is another peak at theta equal to pi. So it's f theta is symmetric about pi by 2. And the other approach normally that one uses for studying phase transition is the Landau phenomenological theory. So you just use the fact that there is a broken symmetry here. Here, in the particular case of nematic, it's a broken orientational symmetry. But in general, close to a second order phase transition, you can always write a Taylor series expansion of the free energy. S can be anything, supposing it is, in fact, a ferroelectric polarization. P is a vector, in which case you cannot have the PQ term because the vector will become minus. So if it is P, it becomes minus P by just rotating the frame of the coordinate system. But that doesn't change the system. But this sign means that if once S becomes negative, this energy will be different. Therefore, you don't want to have the odd power term. And then you will get a second order phase transition at T equal to T star. But in the case of nematic, the situation is different because negative S, you remember the definition of order parameter, 3 cos squared theta minus 1 over 2 statistical average. If you want to get negative S, theta should be close to pi by 2. This means the distribution function now must have a peak near theta equal to pi by 2. And that's a very different distribution function compared to the one that I showed earlier. So positive and negative autoparameters are distinctly different. And therefore, you must keep that. In fact, this was the first main contribution of de Gennes to this field. So it is now called the Landau-de Gennes free energy. And once you have a third order term which is non-zero, this leads to a weak first order transition between S equal to 0 and S non-zero at a finite value of S. And the strength of the transition depends upon this coefficient B. And it's a very weak first order transition with heat of transition about 1 kilojoule per mole. And then there is this transition occurs at about 1 degree above T star usually, the T star that is defined in that Landau energy. Of course, S can be measured using the anisotropy of any physical property which has the nature of a second rank tensor. For example, anisotropy of diamagnetic susceptibility. Of course, short range order effects have to be taken into account in any molecular theory to get a better model. And I won't go into that. So you then, like in magnetism, take first nearest neighbors and then define a local short range order and then say the whole group is subject to the mean field and so on and so forth. So one can develop that kind of models in the molecular theories. Of course, once you have an order, you have a relevant elastic response of the medium. Of course, here you have an orientational order. And therefore, you have what is called curvature elasticity. See, the vector is a vector in spite of the fact that it is an apolar vector. Any vector field has only two spatial distortions. One is the divergence, which is itself a scalar, of course, divergence of n. Then you have curl of n. Curl of n itself is a vector. So you can either have an n parallel to the curl of n, that defines this twist distortion, or n perpendicular to the curl of n, that defines the bend distortion. So these are the three fundamental distortions of any vector field: splay, twist, and bend. And this is the way, anyway, you write that as quadratic, this distortion, the free energy density. Of course, n is taken to be dimensionless, the director, and therefore you can estimate what is co. Of course, nematic is a soft material, and therefore you can simply estimate it as some thermal energy divided by some molecular. Sorry. So that will come out to be around 10 to the power of 7 minus 7 dyne, which is a piconewton, which is the order of magnitude that you measure for a whole lot of systems. It's of course a very weak elasticity, and that is why there is a big LCD industry worth about $300 billion, dependent upon this 10 to minus 7 dyne, the elastic constant. Of course, in the usual nematics, the bend elastic constant is greater than the splay elastic constant, which is greater than the twist elastic constant, purely for geometric reasons. I leave that as an exercise for you to figure out why it is. Please.
They are continuous, but twist look like it is discrete.
No. It is not discrete because that's the only way I can draw a picture. You assume these are the this is a director field, let us say. As you go in a direction perpendicular to the plane in which the director is aligned, it twists continuously. Of course, finally, there is a discontinuity due to the molecules. That is different. Of course, these are continuum models where you treat a continuum field, right? Okay. Direct is a continuum field. Any other doubts? Okay. So the weak curvature elasticity leads to strong director fluctuations. In a one constant approximation, the free energy density is just some k, average k, grad squared, grad theta squared over 2. So what you do, this is a typical way you handle such a problem. We will see a couple of examples later. You Fourier analyze theta as theta q e to the power qr. Then you know the free energy corresponding to a particular q. Then you apply the the fact that average thermal energy per mode by equipartition theorem is just kBT by 2 per mode. And therefore, theta squared q average you get like so. And then you see immediately that this diverges as q goes to 0. So long wavelength fluctuations are extremely strong. That is because A that sits here is extremely small. Then in real space, you can go back, go to a sphere of radius pi by r, where r is your size of the medium, let us say, and L is a molecule, some molecular dimension, a cutoff wavelength, cutoff length. Then you can go back to the real space and you get kBT or 2 pi kL, where L is that molecular dimension. This is, of course, a finite value, which only says that the orientation order is long-ranged, though there are strong fluctuations. So now that we have defined three, okay, please.
Theta is theta or theta, delta theta?
I beg your pardon?
There in the last slide, is delta theta average over is the fluctuation
now
of
this is theta squared average, right? Because I am just Fourier analyzed theta. So and then I applied the equipartition theorem. So therefore I could calculate theta squared q, and then I went back to real space. This is a very, again, it's a very standard technique that is used to go back to, your fluctuation amplitudes in the mean field approximation, basically. Okay, is that clear?
I was thinking this theta in the Fourier expression would be the fluctuation of the theta average, fluctuation of the director over the average.
No, you see, we started with the free energy expression, right? So that has just grad of theta, which is theta is not the angle made by the molecule, sorry. Maybe that is where you are getting confused. Theta is the angle made by the director in a. So I'm sorry if there is any confusion, let me be clear. You see, originally, unfortunately, you don't have too many angles, symbols for angles, which you use in this particular area. Theta originally I used as the orientation of a given molecule with respect to the director. Here I am using it in the sense that theta is the change in the orientation of the director in space. So you start from some, let's say, some place where it is aligned in a particular direction. Then I see how theta varies as I go along different directions. Is that, sorry if I confused you. So now that we have three types of distortions possible, well, the molecules themselves can encourage it, hopefully. Chiral molecules I'll come to soon. It's a special case. But there are other two types of molecules which you can think of. These are, molecules which look like a spade already, or banana shape, which is bent. Of course, if I take an undistorted nematic, these, compensate for the shape, and you get an undistorted director and no deformation in the medium. But supposing I apply a deformation, then these will adjust themselves to fit into that. This is an exaggerated picture. Obviously, there will be some in the other direction and so on. But I am just trying to make a cartoon of this. Similarly, the banana. But notice that both of these are now polar vectors. There is an n divergence of n, which is a polar vector. N is an apolar vector, but n divergence of n is a polar vector. Again, figure out why it is. Similarly, n dot grad n, which is equivalent to curl n cross n, is again a polar vector. And you can see that it is a polar vector. In fact, something like this is a polar vector. And now, somebody called Mayer for his PhD thesis realized this. He's a well-known liquid crystals physicist. He said, supposing I now have dipoles, electric dipoles oriented so here, then this will lead to a polarization. He called it piezoelectric polarization, but it's called better called flexoelectric polarization. Similarly here. So though n is a polar, once you have either splay or bend distortions, that leads to polarization. But he looked at this specific type of molecular shapes to get those results. But later on, that was 1969, as I said, it was his PhD thesis. Jacques Pro and Marcero. Pro, you might have heard his name in various contexts. Marcero at the time was a student. In 1977, realized that you don't need all this, because any molecule, any anisotropic molecule like this has a quadrupole moment. And let's write a chart. This I have taken directly from that paper, this picture. So it looks like this. This is a quadrupole moment. And it has no fancy shape, right? And it is no dipole moment. But the moment you have a splay, divergence of quadrupole density is a dipole density, just as we are familiar with the fact that divergence of polar, that is a dipole density, is a charge density. So this is very similar to that. Divergence of quadrupole density becomes a dipole density. So flexoelectricity is a universal property of all nematic liquid. You don't have to have anything special. That's the message there. And in fact, in such a case, the flexoelectric coefficient that I introduced last time, but I am going to show again later, it is the number density into the orientation order parameter into the quadrupole moment of one molecule. And we can even estimate it. So the flexoelectric polarization as defined by Mayer is E1 and divergence of n plus E3 curl n cross n. Both are polar vectors. So as we estimated k, we can again say it's charge over length. So some electron charge over molecular length, which gives you 10 to the power of minus 3 CGS units, which is the type of numbers you get if you make actual measurements. So it's again a signature of the soft nature of nematic liquid crystals. And I want to put up this thing with this called Freedericksz transition. Freedericksz was a Soviet, that's Russian physicist in 1930s. He originally did this experiment, so it's called Freedericksz transition, and this is at the basis of all liquid crystal, the entire liquid crystal display technology. So what you do is, align the nematic director, let's say, between two glass plates, and the medium has got positive diamagnetic susceptibility anisotropy, which means if I apply a magnetic field, the director would like to align along the field. That is the meaning of that positive sign. So you have strong anchoring at two surfaces at z equal to plus minus d by 2 in liquid crystal displays. What is done is there are some very special polymer materials, of course, whose obviously we don't know which are those particular materials, supposed to be a trade secret, where they can gently rub it in one direction, then the director aligns along that with a strong anchor. That means you cannot disturb it by the applied magnetic or electric fields that we are going to use. That is the meaning of that practically. In fact, you can even define what is the meaning of strong and so on, which I won't go into. So apply the magnetic field in a direction orthogonal to this. Now it wants to distort because n wants to be parallel to field. That can happen only in the middle of the sample because the strong anchoring at the two surfaces. So the initial orientation distortion, we can just for very small theta. Again, theta is the, sorry, I hope it's clear. Theta is the angle made by the distorted thing with the undistorted. Okay. So I can simply write it as theta naught cos pi z by d. This means it goes to 0 at the two surfaces. So I know what is d theta by dz. The free energy density becomes, you can see that the initial distortion will only splay. So K11, which is display elastic constant, d theta by dz squared. And then this is the magnetic energy, which has a negative sign because that depends upon the angle made by the director with the the sine theta is the other angle. So I have to take sine theta, sine squared theta. So I can then calculate the average energy per unit area. Sine squared pi z by t and cos squared pi z by t is half in such a problem. So there is what is called a Freedericksz transition HC, beyond which the negative wins over the positive energy. So there is a distortion. Up to that threshold field, there is no distortion. This is very much like a second order transition, the Landau energy that I wrote. Instead of temperature, you have the field here. That's the only difference. Of course, if you want to see what happens beyond the threshold, you have to go to the higher order terms. So this is the threshold field. This was done in the 1930s by Freedericksz, this Russian physicist. And that's what is used instead of magnetic field, of course, you use electric fields. So this is a typical way the display works. This is called a twisted nematic liquid crystal display. What you do is, instead of having parallel, that's two surfaces where the rubbing is parallel, the top surface has the orthogonal rubbing direction. Then the elastic response necessarily rotates the director by pi by 2 in the ground state. Then there is a thing called adiabatic theorem in physics, which says if, in fact, I don't know how to put it very well. If the cause is varying very slowly, the response follows. That is the meaning of adiabatic theorem. So what that means in this practical case is if the optical phase difference is much larger than the rotation angle, then what happens is the polarization, this is the polarization of the light beam, follows the director. So that is rotated by pi by 2. So if I put it between two parallel polarizations, it will be cut off and you have no light coming. Now, this has now a positive dielectric anisotropy, just as we had positive diamagnetic anisotropy. So if I apply an electric field beyond that Freiderichs threshold, it starts to deform. If I go a few times that threshold, most of the director is oriented along, except very near the boundaries, where the anchoring is strong. And now you have lost this pi by 2 distortion of the director field. So there is no rotation of the polarization, the polarization of the light beam. So between cross polarizers, it is cut off. So you have a cell in which there is no light and there is no field. 3 times the threshold, you get bright light. That is the basis for the liquid crystal display. And I won't go through the other details because it is not something on technology. So nematic liquid crystal is a liquid because there is no periodicity of any kind, just an oriented liquid. So it should flow. Isotropic liquid, of course, is characterized by a single viscosity coefficient. But the viscosity of a nematic depends upon the orientation of the director with respect to the various other flow phenomena. For example, if I take a shear flow, bottom plate sheared with respect to the top plate. Now there are two directions. One is the velocity, the other is the velocity gradient. Your director can be oriented in various directions with respect to these two. In fact, Polish physicist named Mizowiecz did these experiments in the 1940s. What he did was to apply a very strong magnetic field to orient them in different directions. The first one, the director is oriented along the velocity gradient. The second one, it is oriented along the velocity direction. The third one, in a plane in a direction orthogonal to this plane. And you get three different numbers. There is anisotropy of viscosity. These are called Mesovick's viscosity coefficients. The point is the orientation of the director is coupled to flow because it's anisotropic. If I have a shear, a velocity gradient, the orientation of the director responds to it. And a very detailed analysis shows that you really require 5 independent viscosity coefficients. This analysis was done by Leslie in Britain. So these are called Leslie viscous coefficients nowadays. Not this particular combination, the original thing that he derived from fundamental arguments. So let me just pictorially give you some idea of. See, there are two possible talks. One is, let me start with this. A torque which is dependent on an elongational flow of the medium. So this is connected with A, which is the symmetric part of the velocity gradient tensor. And this torque is given by some coefficient gamma 2 into this n cross n dot A. A is a tensor. The other one is connected with the antisymmetric part, and that is, you see, written here, antisymmetric part. And n, which is defined like this, is the relative angular velocity of the director with respect to the background fluid. In hydrodynamics, you have to worry about frames of reference, how you define velocities, and how you define torque, etc. becomes more and more complicated in a liquid crystal compared to that in an ordinary liquid, which itself is pretty complicated. So this is what that represents. So this is another torque, and there is a different coefficient gamma 1, n cross n, where n is connected with this object, where omega is the vorticity or the antisymmetric part of the velocity gradient tensor. So, people, anyway, I'll come to that. The relaxation, see, liquid crystal display, after all, responds to this viscous response. If you switch off the field, what is the time it takes for it to go back to the origin? That's one question you can ask. The relaxation time when you switch off the field goes as some gamma, which is one of these coefficients. This is called a rotational viscosity, into thickness of the sample square divided by pi squared k. K is, after all, one of some average elasticity relevant to that particular geometry. This turns out to be, used to be 20 millisecond for thickness of 5 micrometer. But I think now there are some better materials. I'm told it goes down to 10 milliseconds or so. So it is not a very fast device, which is an advantage for line by line addressing. But as I said, this is not on technology, so let me not go into it. Now, the spontaneous fluctuations of the director, of course, give rise to a strong scattering of light. So what I can do is that I can write generally, how does a given mode of a wave vector q relaxes? And that is, the rate is given by some orientational diffusion coefficient, which is given by this k by gamma into q squared. And this diffusion coefficient is of the order of 10 to minus. I'm sorry, I'm an old timer. I use CGS system. People who are interested can see how to convert that to MKS. I've never got used to MKS system. So this means that I can use different light scattering geometries. And if I have measured all the 3 elastic constants using 3 different geometries, as I showed earlier, Freedericksz transition, then I can actually measure all the 5 Leslie viscosity coefficients. This has been done. I think the numbers come out to be of the order of 0.5 times that of water at room temperature, about 0.05 pies. You see, again, CGS. Now, the third thing that I didn't talk about, I'm told you have already heard a little bit about this, is if the molecule itself looks like a spiral spring. It's called a chiral molecule. That is, there is a handedness. Of course, to get such chirality, you have to just have 4 different substituents on this tetravalent carbon atom. Then this is a chiral carbon atom. What all you have to do is to, I think the reason is very clear from this picture. The reflection of this green ball is looking in the opposite direction. Therefore it's chiral. So if you have such a carbon, then the molecule as a whole becomes chiral. Very good examples are any biological molecule for that matter. So once you have this, I'm quite sure you have seen such a picture before. The chiral interactions between molecules lead to a cholesteric liquid crystalline phase, which twists, and the pitch of this helical structure is of the order of wavelength of light. Therefore, it reflects light. And in fact, Bragg's law becomes applicable in the visible region. And I think probably you might have seen this picture again. Beetles and so on, they have such a structure in their wings, helical structure, and therefore they show this iridescence. Iridescence of beetles mainly is because of this optical effect. Now, the spontaneous twist, you can say, okay, why is it only in one direction? There is a chiral interaction. So in principle, I must have it all around a given direction. I put a director some point in vertical direction, go around it. Why should it twist only in one direction? In principle, it should twist in all directions. But then this double twisted structure cannot lead to a uniform phase, obviously. You see, this goes on like that. The only thing that can happen is such double twisted cylinders should arrange themselves in some spatial organization. Only then this is feasible. In fact, many of these figures I am taking, this is a very good book for those of you who want to, because there are several books. One was written by Chandrasekhar, who was our mentor in the Raman Research Institute long ago. It's seen a second edition. So that's, it emphasizes molecular properties. De Gennes wrote a book on the physics of liquid crystals. It was revised by Jacques Pro. That's again very good. But then post-De Gennes era and post-Chandrasekhar era, for that matter, is covered very well by two books by Oswald and Piranski. Their first book is called Nematic and Cholesteric Liquid Crystals. The second one is called Smectic and columnar liquid crystals. In fact, all the more recent developments are very well described in those two books, and experimentally oriented as well. So this structure involves also a bending of the director. You see that. You see the director bends. It just cannot twist. It has to bend. Now, once we know that, in fact, long ago, in the 1960s, cholesterol nonannate was already known to have 3 different phases above the cholesteric liquid crystalline phase before it became fully isotropic. But look at these temperatures, just 0.3, 0.4 degrees, BP1, blue phase 1. Then another blue phase, another 0.1 degree or so. And yet another blue phase, again another 0.1 degree, then it becomes so very narrow temperature. In fact, this Piranski is again an excellent experimenter actually. He grew single blue phase crystals. I call them crystals because I'll show you what is the structure of these in the next slide. And if you shine monochromatic light, laser beam, these are the sort of Cosell diagrams that you get. This is typically how you find out what happens, what's the symmetry of a crystal. For you shine X-rays, you get the Cosell diagrams, if you have a single monochromatic beam. This is now in the visible region, of course. Now, these are you see BP1, a structure of BP2 has O2 symmetry, BP1 is what is called O8 symmetry, but you can see that these double twist cylinders are arranged in specific fashions in these two. Both of them are cubic crystals. And in this junction of these two, you can easily see that the director has a disclination. Now, I had shown you a disclination in which it went like that. That's called a positive disclination. This is a negative disclination where the director field has this type of structure. So the disclination line is this is the projection of the disclination line in the center. So this is the negative half disclination. And since it's a topological disclination, the center of the disclination should be in the higher temperature phase, namely isotropic phase. So there is an isotropic to cholesteric interface. Sorry, why? The rods, in fact, I'll come to, I think I'll very briefly mention this in the next slide probably. The rods have to be arranged somehow in some arrangement. There's no other. The blue phase 3, it is something like glass, arbitrarily arranged glass. But as you go to a lower temperature, in fact, one term that I'm going to introduce now will ensure that the energy is minimized for these structures. Anyway, let me come to the next slide. You see, the elastic energy density that I introduced earlier involves some grad theta square, right? Now, to the same order, you must have grad square theta in there as well. Same order, Sorry. I think, yeah. You see, the relevant term is a divergence of these two things which went into the flexoelectric. N divergence of n is a vector, n cross curl n is also a vector. So divergence of this term. So since this is a divergence of some polar vector, it's a surface term. And usually you can ignore it in most problems. For example, Freedericksz transition, you don't care because you have firmly anchored director at the two surfaces. The blue phase, of course, is full of interfaces. I showed you, that there are disclinations whose cores are in the isotropic phase. And the relevant term, therefore, has this form minus K24, which is the coefficient of this. This is also sometimes called the saddle splay term, which I might come back to later on in some other context. But that's another term that you will find in the literature. It's the same thing, actually. So this has the form delta nx by delta y into delta y and y by delta x. The twist distortion in those double twist cylinders is a constant. So if you calculate this energy density, it becomes so. That is, there is a price that you pay due to the twist elastic constant plus this K2. And then what these four people showed back in 1981, so I can also point out that one of the authors was P.W. Anderson. Here, I'm quite sure most of you are familiar with his name. He got a Nobel Prize for his work on Anderson localization and so on. So he was somehow interested in this problem. So the net energy, which has this K24 plus 2K22 in the bottom, and also K22 into K24 here, this actually becomes negative if K24 is actually negative, and it lies within this range. So this double twist cylinder itself becomes now a feasible, that is a structure which has a lower energy compared to the single S twist cholesteric phase. Then I'm not going into this. I think there was subsequent work by people called Myboom, and somebody, Myboom is also in this, associated with some other group, who showed that this can only be arranged in these two lattices, because they considered all kinds of lattices, and they found that this is what minimizes the energy, and that corresponds to the experiment. So why particularly cubic lattice, I cannot directly answer, except to say that they have taken into account, for example, they try to put them as a set of parallel and that will never work. And because you will then get a very different type of issue. So they then showed, that is not this group, but Mayboom and I think there's a German scientist whose name I forget. And they showed that the cubic lattices are the ones which minimize this energy. It's a pretty longish calculation anyway. So now, supposing I take a rod, and normally the rods are made of an aromatic core, which is a few benzene rings lined up, which has a very high polarizability anisotropy, and Meyer-Sope pointed that out, and that is what causes the nematic orientation order to be stable. And then there are two aliphatic chains, CNH2N plus 1, basically. The single bonds, the chain. These have much lower polarizability compared to the aromatic cores. So in the nematic phase, anyway, there can be some mixing between these two parts. There is an entropy advantage. But then you lose the dispersion energy, because that depends upon the quadratically on the anisotropy of the polarizability square. So this dispersion interaction depends upon the polarizability anisotropy. The square of that, which is a negative term, that will be prevalent only if these two are close. So if the chain is very short, then the entropy wins over and you get the nematic phase. If the chain is very long, this is not a good idea, especially as you decrease the temperature, the entropy contribution reduces. Then it is this biphilicity which favors the formation of layers, but liquid layers. So this has got one-dimensional periodicity. That is the director. And these are called smectic liquid crystals. Smectic A is one in which the director is parallel to the layer now. And in fact, Macmillan pointed this out in fact, I must go back in history a little bit. See, Jacques Friedel, in the 1920s, he saw a texture of this, which I will exhibit in the next slide. And he immediately said, this must be a layered system. And Macmillan actually, sort of extended the Meyer-Sope theory, introduced a coupled order parameter, which is that Meyer-Sope order parameter multiplied by cos 2 pi z by d, which is the translational order parameter, and the statistical average of that is the order parameter for this medium. And he sort of the same, I am not going to repeat it. Once you have the single particle potential, you know everything else. Same procedure. So I'm not going to repeat the procedure, except to say that back in 1920s, this is what Friedel saw. An ellipse, and this is actually a hyperbola. And you can see in some other sample, that is the hyperbola, and that is the ellipse orthogonal to this. These two cross each other at their foci. These are called focal conic structures. And the way they originate is the following. Supposing I have a torus type of thing, these are layers. And supposing I have a torus, like a tube made of these layers. Then you can see that there are only two discontinuities in the director field. One is at the center of this torus, because the director is trying to orient from all kinds of directions there. And then a straight line perpendicular to the place where these two touch, because there is a discontinuity there. And if you relax these two, that is, supposing your torus has got a smaller diameter on this side than that side, you end up with this ellipse and the orthogonal hyperbola. This is well known from geometry. So these are called focal conic textures. And if you see this, you know you have layered system according to Friedel. Again, I will amend this tomorrow. Of course, then you can ask, what is the elasticity? Then they have two types of order. One is a one-dimensional periodic order, and the other is, of course, the orientational order. They are like molecules. So this you have mixed elasticity. So if I define a displacement vector u, then you have a longitudinal mode and a transverse mode possible. This depends upon delta u by delta z being not equal to 0. And this corresponds to really the Young's modulus, the compression modulus. And this one is this play deformation of the director field. So you have these two elastic constants. B is something like Young's modulus 10 to the power 8 dynes per centimeter squared in a soft material like this. Kn1 continues to be about 10 to minus 7 or 10 to minus 6 dynes. It's force, units of force. The free energy of the sample, we can go through the same type of analysis again. So you have got grad ZU, and then I take out a B, then I get a length here. This is called the penetration length of this plate distortion. And you go to the Fourier space, you analyze U in terms of its Fourier components. Again, apply equipartition theorem for each mode, and then go back to the real space. What do you get? You get this result. U squared or statistical average is KBT logarithm, note that logarithm, of QC. QC is cutoff wave vector, again molecular dimensions. L, which is the thickness of your sample, divided by 4 pi lambda into B. Lambda is that penetration length, B is the Young's modulus that I defined. Now what you must notice is this goes logarithmically as the size of the sample. This is the famous Landau piles instability of one-dimensional systems. It has no true long-range order. It's what is called a quasi-long-range order, because U squared R, statistical average, diverges logarithmically with the size of the sample. You can ask, what is the dephasing length? Dephasing length, I can say, is roughly, when U squared R, it's roughly like the, say, layer spacing squared, for example. Then you just don't define a layer at all. That turns out to be of the order of tens of meters if you sit down and calculate. So you can always make a thin sample, 10 microns in thick, and happily conduct your experiments, no problem. So thin samples you can conduct. So anyway, nobody has made enough Smectic materials to fill up, say, 10 meters size, so no problem escaping from this order. Of course, both twist and bend distortions which involve Curlin will change the layer spacing. Layer spacing changes will require the B elastic constant, that is the compression elastic constant, which is far higher than the curvature elastic constant. So these are essentially disallowed in the sample. Then De Gennes in 1971 realized the following, that this is a density wave actually, so which has two components. One is the magnitude, the other is the phase of the density. And immediately he recognized an analogy with superconductors, because the wave function of the Cooper pairs again has a phase and an amplitude. So once you recognize that analogy, many things follow. So you can write the Landau-Ginsburg free energy near this Smectic nematic transition. This is the usual order parameter square, the quadratic term and the quartic term. And then there is this gradient, lateral gradient of the order parameter, which has to be written like this, because this is the relative rotation of the director with respect to the layer norm. For example, if I take this and just rotate the whole thing, free energy cannot change. So it's the relative rotation that is important. So that is why you need this delta minus IQ naught delta n perpendicular. Then, of course, you put the three elastic constants. Therefore, there are two, you can using this define two lengths. One is the coherence length of the outer parameter, which comes out like this. This alpha is the coefficient of the quadratic term. And then the penetration length. I had defined a penetration length of only display, but for the curl distortion, this is the penetration length. Both of them have alpha in the denominator, square root of alpha. So the ratio is independent of the temperature. If this lambda, which is the penetration length, is less than zeta by square root of 2, you call that a type 1 material, which directly goes from Smectic A to nematic phase if I try to apply a very strong Curl distortion. So the Curl cannot penetrate, it just goes from. So this is like the type 1 superconductor. On the other hand, in a type 2 material, which has the other inequality, for a range of values of Curl, edge or screw dislocations can be created in the medium. These are like vortices in a superconductor. See, this is a layered material, so you can talk of edge and screw dislocations. Both of them involve curl of n. Then the best method of having a natural twist distortion is to have chiral materials. We have already talked about them. So in 1988, Wren and Dubinsky argued that in a strongly chiral type 2 medium, the following type of twist grain boundary phase can be stabilized. They worked out this theory. See, here these are blocks within which you can define the layering order very well. There is a twist across blocks, across a grain boundary. The grain boundary is made of a set of parallel screw dislocations. Each screw dislocation looks like that. And this is again, I've taken this figure from this book. And this was in 1988. I think without the knowledge of the theory, some people had already discovered this around the same time. So Goodby, which is a very well-known liquid crystal chemist from Britain, and his colleagues in Bell Telephone Labs had already found this. What did they find? They found that this material, which has a chiral center, between the Smectic and cholesterol phase, this material exhibited a medium with sharp Bragg peaks corresponding to the layering order, and then optical properties which corresponded to a helical twisting. So they didn't know how to analyze that. In fact, they were struggling. Then they realized that here is a theory which already gave that model. So it was a good coincidence. And subsequently, much later, 1998, this Neville et al. In France found a material in which there is a commensurate helical twisting compared to the block size. So this means if I take a well-aligned sample and take a picture, you can see these each correspond to a block which is twisted by some angle compared to the rest. If it is incommensurate, it will of course average out. So you won't see that. Only in 1998 they got it. Of course, once this was discovered in 1989, 1991 Nobel Prize in Physics was awarded to de Gennes, partly, of course, only for his contribution to the physics of liquid crystals, because he has also contributed to magnetism, superconductivity, polymers, and also wetting phenomena, and so on. So, but in fact, I know that a lot of lobbying is done by the liquid crystal physicists for his Nobel Prize. Anyway. Of course, also you talk of first and second sounds in superconductors. So there is a correspondence in Smectic liquid crystals as well. First sound corresponds to density variations without change of layer spacing, whereas the second sound is the other way. And in fact, these can be seen by balloon scattering. This experiment has been done. And this strongly depends upon the angle between the direction in which the that is the angle between the Q vector and the layer norm. Anyway, I won't go through those details. These are again in various books. So now I come to a different Smectic liquid crystal. In some, the molecules can tilt with respect to the layer norm. If the tilt angle omega is 0, you get Smectic A. These are called Smectic C liquid crystals. Now the question is, why do the molecules tilt? This is a very, in fact, took a long time. Macmillan himself had a theory. Anyway, I won't go through because it's a bit murky, this whole thing. So I will just refer to some work that we did. I think we finally have the correct theory. So I'll just, in one slide perhaps, explain this to you. See, if you look at the molecules in which it tilts, by the way, tilting, if you take just a spherocylinder and tilt, the cross section increases, the molecular cross section. In fact, because of this, the entropy decreases. So the hard rod interaction will never allow tilting. So it should be some attractive interaction which is responsible for the tilting. The question is which one? So we realized, fortunately we have had chemists with us, and so could discuss with them and look at chemical structures, try to understand the meaning of these and so on. So this one, if I don't have these oxygen atoms, this is called an you see, this is alkyl azobenzene. If I don't have the oxygens, it has no net dipole moment. It shows only Smectic A nematic. You put these oxygen atoms, it is alkoxyazobenzene, then it shows Smectic C and Smectic A. And you put another oxygen here, it is alkoxyazoxybenzene, then the Smectic C directly goes to the nematic phase. So it's clear that lateral dipole moments are necessary. Macmillan had used a dipole moment, but he used it in the center of a rod. If the rod rotates freely, then the dipolar interaction is averaged out. So what he said was they don't rotate freely to get the tiltings. But then NMR experiments and then neutron scattering showed that the rotation is not completely free, but certainly not hindered to the extent that he required for the formation of Smectic C. So that theory was out. So what we realized was that these dipoles are not on the axis, but off axis. The moment you do that, you see this is the nearest approach of these two dipoles in a Smectic A layer. It's highly repulsive. And this is attractive, but they are far up. And this is again repulsive, but these are even farther. So the net result is the dipolar interaction is highly repulsive if the molecules are freely rotating. So to escape that repulsive interaction, the molecules shift along the direction of the molecular orientation. Of course, there is this dispersion interaction which wants to keep them in the Smectic A phase. So it's a competition between the dispersion interaction and this repulsive interaction. And in fact, we have done some detailed calculations to show that this actually can be the origin of the tilting in the Smectic phase. Because if I shift relatively, it is equivalent to tilting of the molecules. So the Smectic A to C can be at second order transition as well. And de Gennes himself used this tilt angle as an order parameter. And he was a phenomenologist. He was not worried about why the molecule tilt. He just described it using the omega, that is the tilt angle, as the order parameter. But actually it turns out that Smectic C is pretty fragile and can disappear, for example, in mixtures, even though both the components show the Smectic C phase. So according to our model, anyway, it's easy to understand because the dipoles may be positioned in different locations so that they cannot repel each other very well, and therefore no tilting. So you get only Smectic A phase in between. So the two components show the Smectic C phase. And then, again, Kalkura was one of our students. They did some high pressure experiments. They found that Smectic C can be squeezed out at high pressures. Yes, please. No. Sorry. And again, Lubensky, the same Lubensky that I mentioned earlier, there he developed a phenomenal, Chen and Lubensky, this is again a well-known model, a phenomenological model for the Smectic A to C transition. Of course, these are the two Smectic A Landau-Ginsburg terms. And then he introduced these two terms, C perpendicular, grad perpendicular psi. Psi is the translational order, the order parameter of the layering. And then there is a higher order term as well. The reason is, he said when C perpendicular becomes negative, then this tilts because there is a lateral component of the order parameter, of the translational order parameter. And in order to stabilize the system, you need this higher. And this leads to what is called a multi-critical point, NAC multi-critical point, which has a particular topology. And people have studied this, at one time this was a very popular subject. Now, up to now, I've said liquid crystals, nematics, Smectic A, Smectic C, these all have apolar order, no ferroelectricity. Again, this R.B. Mayer, who introduced flexoelectricity, realized now you take Smectic C made of chiral molecules. See, this Smectic C has two symmetry elements. One is a plane, a reflection plane in the plane of the screen, and the other one is a two-fold axis perpendicular to the screen, because the director is apolar. It's a two-fold axis. Supposing the molecules look like spiral springs, chiral, then you lose the mirror plane, which means this two-fold axis should now become a polar vector, because in the reflection it looks in the opposite direction. No reflection plane. And of course, tilt is still the primary order parameter. So what he did was, in fact, he was actually visiting de Gennes at that time. He was a postdoc in Orsay. He realized this. I will not go into a slightly interesting story about it because I think I'm running out of time anyway. So he coaxed a chemist to make a Smectic C with chiral molecules and demonstrated that it had ferroelectric order. The primary order parameter continues to be the tilt, and this is a secondary order parameter because it comes out of this basic symmetry argument. Only because of this symmetry you get polarization. It also means the molecules do not rotate as freely in Smectic C star. See, star means chiral, by the way, as in the Smectic C phase. But of course, it also leads to a helical twisting. So it's a helielectric phase. So in a macroscopic sample, there is no polarization. But Clark and Lagerwall in 1980 showed that if you have a thin enough sample, again, the pitch there is something like say 1 micron. If you take a sample which is of the order of the pitch or less than the pitch, you take a long pitch, in Smectic C star, and take a thin sample, then the helix unwinds. Again, it's a good exercise for you to find out why. And then you get a true ferroelectric. And this can be switched from one to the other. Let me go back to this. You see, if the polarization is looking towards you, and the molecules are tilted that way, if I apply the opposite electric field, the polarization should look into the board, and then, therefore, they have to tilt the other way. So there is a clear change in the orientation of the tilt, and therefore this can be used in an electro-optic device, like a display. And they showed that this change can be brought about. In fact, this is now a DC electric field responding device. So I can increase the field as much as I like and make it as fast as I like. And since it is a Smectic, it has memory. It doesn't come back easily, like in the case of the Nematic. So fast switching, memory. What else do you want in a good display? So in fact, everybody jumped into this field, practically everybody working in the field of liquid crystals, to the extent that they had to start a new series of conferences just to handle the number of papers that were being produced. But unfortunately, the bistable switching, you see all the 100-inch television set that you see in the television store doesn't have this ferroelectric. The reason is very simple. Smectic liquid crystals have memory, not just for what you have done, reoriented, but for any defect that is in. And if you get a large enough device, there will always be defects. Nematic knows how to heal itself because of the strong anchoring at the surface. The Smectic doesn't know how to heal itself. So you cannot make large devices. But maybe probably this projection here is through what is called an LCOS device, liquid crystal on silicon. You can make a very thin, any 1 centimeter by 1 centimeter area device, see it in reflection. I won't go into how it's made. That can be used in a projection display and it can switch very fast, so it has advantages. And of course, I can now ask the question, supposing there is a strongly type 2 chiral Smectic C star, do I get a TGB phase? You say with a TGBA, it was with a chiral material anyway. In fact, the answer is yes. This was discovered by Barwa et al. In 1993. And it so happened we discovered the most complicated TGB-C star phase in 1997, I think that's right. It has this structure. See, within the block of Smectic TGB-C, it doesn't twist. Here we found a case in which there is a twist within the block also. So there is a twist orthogonal to the blocks as well as within the block. So it's three-dimensionally twisting structure. It's a pretty complicated structure. And then subsequent work which, in collaboration with Boulder Group, who have good facility for freeze fracture electron microscopy, shows that this is an extremely, this type 2 material is an extreme type 2 material, where the penetration length is of the order of a few hundred angstroms instead of just about 10 or 15 angstroms in the typical type 2 material. So anyway, now one of the results of this intense activity on the ferroelectric liquid crystals was other types of liquid crystals were also discovered. Chandani, who is actually from Sri Lanka but working with a Japanese group, they found in a material called MHPOBC is the usual bistable switching, ferroelectric switching that I discussed. And at low temperatures, this material shows what is called a tristable switching. The only way they could understand was to say that alternate layers have anti-clinic tilting. This also means an anti-ferroelectric polarization. This is the low temperature phase. And of course, this I can apply a strong field, then depending upon the field, then all of them will align in the same orientation, become a ferroelectric, go in the opposite direction. So those are the two states. If I switch off the field, it always comes back to this. So this is a third state, 3-state switching. In fact, this material, as well as a lot of other materials which were synthesized, showed not just these two, but a complicated sequence of phases, starting with Smectic A. The Smectic CB star is what is equivalent to the ferroelectric Smectic C star phase that I discussed, and Smectic CA star is what Chandani et al. Discussed. But then you have this alpha, gamma 1, and gamma 2. These are 3 ferroelectric phases in which the polarization is lower than that of the ferroelectric phase. So they then developed what is called an axial next nearest neighbor Ising model, which is in analogy with what happens in the magnetic materials, to describe these intermediate phases. But then the point is the following. See, Ising model has only 2 states, up or down. But these are liquid layers, and anyway there is a helical arrangement. So we realized that this is therefore not a good model, and we developed what is called an XY model, axial next nearest neighbor XY model, where it's a 2-dimensional distortion rather than just up and down. And I will not go through this because I see that I will be running out if I try to describe everything. So we introduced various materials. Maybe I'll just spend 1 minute on this. You see, many people thought at that time, okay, if you have two layers, because there is a polarization in each layer, there is an electrostatic interaction between the layers. But it turns out Maxwell had realized this hundreds of years, 150 years ago. If you have a uniform polarization, there is no field perpendicular to it. Again, a good exercise for those of you who are interested in this. Uniform polarization in 2D, there is no field perpendicular. So there cannot be an interaction due to that. And then Jacques Pro and Bruinsma said in 1994, okay, supposing I look at a splay distortion of the polarization field, then div P is rho, a charge, bound charge. Of course, this is negative charge here. Therefore, if there is a ferroelectric layering, this is a repulsive interaction due to the fluctuation, splay fluctuation. But if there is antiferroelectric orientation between successive layers, then this is positive and that is negative. So there is an attractive interaction. So this can stabilize antiferroelectric fields. In fact, this is what stabilizes most of antiferroelectric liquid crystals. I won't go through because it sort of takes me away from. And then subsequently, resonance X-ray scattering studies are made on the Ferri phases, and that supports the AN-XY model. This is Mack et al. 1998 did this experiment. Our model came, I think, in 1996 or so. Anyway. So I'm just putting up the picture of the various intermediate phases. I won't have the time to describe that. So the other thing that I want to point out is that Smectic liquid crystals have also a surface tension, which means it is easy to draw a film across even 1 centimeter gap. And now it's like a 2D liquid. And in the case of Smectic C liquid crystal, you see there it is like a 2D oriented liquid, 2D nematic. So the next question is, can we have crystalline phase in 2 dimensions? I don't know. I think Nelson didn't talk about this, I suppose, because he's contributed to this. Oh, okay. So that's a different problem. So assume a 2D crystal made of cylindrically symmetric molecules with a hexagonal arrangement. UR is the 2D displacement. I talked of the displacement of the layer. Now it's a displacement within the 2D crystal. So there is a symmetrized strain given by this expression, and you can have either shear modulus or compression modulus because it's a crystal. So you go through the usual procedure. UQ squared goes like this, again 1 over Q squared, which means in real space, the fluctuations diverge logarithmically with the size R again. It's only a quasi long range order. A is, of course, the lattice spacing, R is the size of the sample. So if you have a large size sample, there is no 2D crystal. Then Mermin pointed out in 1968 that in spite of this, there could be a long range orientation law. Again, these figures I have taken from this book. So let me elaborate a little bit on this. Edge dislocations are the topological defects in a 2D medium. So you introduce an extra layer like this. So you have one with 5 neighbors, the other with 7 neighbors. This is an edge dislocation. So if I go around this, the energy of the defect is given by the logarithm of L by A. Again, it diverges logarithmically with the size of the sample. So once this happens, you see, you can then count the number of ways in which you can introduce that edge dislocation, and that is L by A squared. But anyway, once I take the logarithm, it is logarithm of L by A again. So you have an entropic contribution, which is logarithm of L by A, and an energy contribution, which is again logarithm of 1 by A. So the free energy, which is W minus Ts, goes as logarithm of L by A, but with a coefficient which looks like this. So below some temperature, these dislocations are bound in pairs. Then the energy is very small, logarithm of R by A. But beyond some temperature, they unbind. So this is the well-known dislocation, unbinding transition invoked by Kosterlitz and Thouless. And of course, they got the Nobel Prize in 2016 for their work on topological phases in general. And this was one of the very important contributions. Later, Halperin and Nelson, you have heard Nelson last week here, they argued that just above the melting point, the positional order is short-ranged, exponentially decaying with distance, but not the bond orientational order. The bond orientational order is now defined like exponential of I656, where phi is the angle, because it's a hexagonal symmetry. This medium is called a hexatic phase. The orientational elastic energy per unit area is then some K6 grad phi 6 squared, like the usual elasticity. And the elastic constant K6 goes like KBT. Again, size squared will turn out to be logarithm of diverging with the size of the sum. It's again a quasi-long range order only. It's a two-dimensional system. But if you go by using the same argument as Kosterlitz and Thouless, if you go to a higher temperature, then it goes to a true liquid. So I will skip this because of the shortage of time, but experimentally these were actually formed. If you take a thin enough sample, high temperature, you get Smectic. This is done by electron microscopy again, by electron diffraction. You see it's smeared out. You go to the hexatic B, you see the 6 diffraction spots but spread out. You go to a lower temperature, this is the two-dimensional crystal with this, of course it's a finite size sample, you see these condensed spots. So this is the sample used and this is the hexatic. If you go to Smectic C, there are other various possibilities. The tilting can be along this hexagonal neighbor or between the two neighbors and so on. So this will give rise to different types of hexatic phases. They have all been discovered. Now I come to the very last part of my talk. I think just 3 or 4 minutes left. The question is, can I have two-dimensional translational periodicity and one-dimensional liquid in three-dimensional space? The answer is yes. And of course, this is the most important discovery made in the Raman Research Institute. These are called columnar liquid crystals, discovered back in 1977 by Chandrasekhar and his co-workers. And its typical texture in a polarizing microscope is called a flower texture, and it looks like this. The molecules are not rod-shaped. These are disc-shaped molecules. And this is the original disc-shaped molecule. It's called hexa-N-heptanoate of benzene. So here is the aromatic core. These are 6 aliphatic chains projecting out of this central phenyl ring. It has the 6 flexible chains are important for the structure. Of course, this can again arrange later on. The people found that it also can form a nematic phase, but with very different properties compared to the nematic phase made of rods, because the director is that way, and the for example, the polarizability is much larger orthogonal to the director rather than parallel to, and so on. So this is the columnar phase. Two-dimensional crystal and one-dimensional liquid. The liquids are, the columns are liquid. The question is why? The answer is very simple. If I take such a crystal and heat it, the chains sort of become extremely flexible, which means the correlation between columns is lost, which means each column is now a one-dimensional object. Landau-Pils instability, which means there is no periodicity along the column. It's a liquid column. I hope that's clear. So it's a liquid-like order along the column. The usual analysis shows that the order has now true long-range order. There is not a quasi-long-range order. Again, you can sit down and work it out, straightforward. Of course, subsequently, several, this already shows 0. I was looking at this clock, I'm sorry. Not very precise, very good. Good. Just a couple of more slides and I'll stop. See, people have found various other, you see, this is the hexagonal two-dimensional lattice. There is also a rectangular lattice. This is called herringbone structure because the molecules are tilted with respect to the column axis, and the tilt goes the other way around in the central disk and so on. And one can again write the free energy. There's, I think, like in any other two-dimensional crystal, you have got a compression modulus, a shear modulus, and then the usual bending modulus. And the textures are fairly complicated. I showed a flower texture. And in fact, they can even bend in very complicated fashion. The only curvature distortion is the bending of the layers, which will preserve the intercolumnar spacing. Nothing else is allowed. So if you have that restraint, you can see what are the possibilities. And unlike in a smectic, smectic can be drawn in films, thin films, 2-layer films you can draw in 1 centimeter square. This cannot be drawn because it's a two-dimensional crystal. You can only use a pin and get a thread. And the columns will be oriented very well along the thread there. And this can be used in, for example, X-ray scattering and mechanical experiments and so on. So this has been done by, originally showed by Van Winkle and so on, Clark's student back in 1982. But now many people have done similar experiments. Now I think this is going to be the very last thing I say. Both rod-like and disc-like molecules are relatively simple, mainly biphilic in nature. There is an aromatic part, there are aromatic chains projecting out, biphilicity. That's how they are organized in those two, either layers or columns. Now, what happens if the molecules are polyphilic? There are different types of groups, chemical groups, which have their own affinities. For example, a fluorinated carbon chain which doesn't mix with a hydrocarbon chain. This is known in chemistry, hydrogen bonds. So you can really make things quite complicated. And, Carsten Tschirske, who works in Halle, is very good at this. He's a very good chemist. He has written several reviews in chemical reviews on this work. He has made a large number of those. I will just illustrate it with one before I stop. See, look at this molecule. It looks simple. There is a hydrogen bonding between this OH and that oxygen between different neighboring molecules. There is an alkyl chain. R stands for the chain. Then there is this aromatic core. So triphilic rather than biphilic. What he has shown is as you increase this chain length, for relatively small chain lengths, you get a Smectic C. Then it gets distorted. You go to a columnar phase. The only thing you are doing is increasing the chain. Various lattices, hexagonal, then rectangular, center rectangular, different types of rectangular. Then some kind of a broken layering. And then back to what is called a columnar. I'm sorry, again a layering order. Then a cubic phase, which I haven't discussed. And finally, back to a columnar liquid. The only thing that is happening from there to there is the chain is increasing in length. So you get very complicated changes. I think I'll stop at this. Tomorrow I'll talk about things that have happened after all these things, the more recent advances in this field. Thank you very much. So, I don't know, questions allowed normally?
Thank you so much, Professor, for the nice talk. Now, time for questions.
I have, so recently I started working on liquid crystals.
Oh, that's good. Where do you work?
At Thapar Institute, that's in Patiala.
In?
Patiala.
Oh, that's good.
Yeah. So mostly I work on two-dimensional systems. Again, just last few slides that you showed. Yeah, so those things. So I was thinking, if I have a surface and I have these ellipsoids, so the anchoring is parallel or perpendicular? That depends on what?
You see, actually, that's why I told you, when you make the liquid crystal display, you want the molecule or the director to be parallel to the surface. So the trick doing this is called Chatelain's technique. Chatelain was a French physicist. He found this technique in 1950s, I think. So you take a piece of paper and rub it. He didn't have any other fancy thing. There was some, I say your glass plates, however well you clean, there are some deposits. So you form some grooves. Then the elasticity demands that the director becomes parallel to the groove direction, because any other orientation there will be elastic distortion. So that is what is used even today, except it's extremely sophisticated. You first coat it with some polymer. I think there are some aligning agents. I think there's a Japanese company, name I forget, and even an American company, I think, which sell these aligning agents. So you have to make a thin film deposit. So what normally is done is you take a solution, then you put it in a rotating table, like in a centrifuge, you can make a table and rotate it so that it's a very thin film, let the solvent evaporate. So that, and then let it polymerize. These come as monomers. There is some either UV or some such thing, it polymerizes. Then you rub it gently along one direction. There are rubbing machines. One of my students, I think Surajit Dara, who is in Hyderabad, he even made some rubbing machines. I think I don't know whether they still make it. They even sold some. So then you align it. This is even in technology they use it. The 100-inch television set that you see, the alignment is done like that. If you want to have a particular alignment, it is called homeotropic alignment. The technique is different. It's octadecyl some dimethyl something, which has got, octadecyl means 18, right? 18 carbon atom long chain, which at the other end has something which sticks to glass. So then these are actually looking up like that. So your rod-like molecules fit into that particle. And in any case, all of them have aliphatic end groups, so they also fit in properly. So you get the orthogonal alignment. In fact, again, I think the technology is not the subject in this school. You, in display device, you don't want that to be parallel. The reason is very simple. If I apply an electric field, should I tilt this way or should I tilt that way becomes a problem. In fact, they tilt both ways. So you get defects. To avoid that, you have a pre-tilt, as it is called, 2 or 3 degrees. And these particular polymers are supposed to give you 2 to 3 degree pre-tilt when you rub it with some force. So I think it's a pretty sophisticated technology from the technological point of view, but I think in the lab you can certainly, you are doing experiments, is it? Or are you doing theory?
Recently, one of your students from Kararai, he joined in our institute. So he is an experimentalist. Khan. Rajkumar Khan. But I do simulations. So
oh, you do simulations.
So we were thinking we probably could do something.
Okay, simulations, probably, I don't know if you put surfaces. See, most probably your simulation will first give you the parallel orientation.
Yeah, absolutely, all the time.
Yeah, that's the only thing probably this is because of entropic reasons, most probably.
Yeah.
So there is no way of getting a hard rod simulation to get molecules to be parallel to the surface. You must put in some attractive interaction.
Other questions?
Yeah.
Yeah, so the rod-like molecule has been used in displays.
Yeah.
So I was wondering, what is the advantage of these bent core molecules in
Tomorrow. Wait. And see, when I used to be young, there used to be films in the theaters, and I come from Mysore. We have what are known as jatkas, the horse-drawn. So there used to be advertisement. They will say, to see the rest, come to the theater tomorrow. So that's what I'm saying. If you want to hear about bent core, attend my lecture too.
Are you also going to tell us about the effect of shear flows on, say, the transitions and?
Hydrodynamics of nematics is a horrible subject. I'm sorry.
Smectic is even worse, I suppose.
Yeah, Smectic C. In fact, Smectic C, I didn't mention anything about its elasticity. In fact, it's a fairly complex elastic response, obviously, because you have the elasticity of what is called the C vector. So the projection of this tilt in the plane of the layer is called the C vector. And it is a polar vector, by the way, because if I project this way, it's oriented that way. If I project the other way, it's oriented the other way. And so the curvature distortion of the C vector field is one thing. Then you see you have the usual layer displacement U that costs energy. There is a coupling between these two that costs more energy. And then in a Smectic C, a twist or a bend within a layer can get coupled to a twist across the layers. In fact, this can give rise to some spontaneous breaking of chiral symmetry in some growth patterns, which we again found. We were the first to find it about 20 years ago, and we were the first to measure that relevant elasticity. So Smectic C is pretty complicated. So you are interested in flow of Smectic C?
Well, we tried doing some experiments, but they were very difficult to analyze.
In fact, to get orientation on a well-oriented Smectic C is not easy. Even nematic can become.
Geometer, it's quite impossible.
Yeah, it's practically impossible. So this was a thermotropic Smectic C, is it? Oh. A2CV is only Smectic A, not C.
It was a long time ago and it failed.
You see, Smectic A viscosity is very, it's a two-dimensional liquid. So within the liquid, it's a sort of 0.05 poise kind of thing, but across the layer, it's now one-dimensional periodicity. So it is a jump-like motion. It's called permeation. And the viscosity effectively is 1,000,000 times larger than in this direction. So that can cause a lot of problems in flow phenomena. In fact, it can even lead to a plug flow and so on.
If you have more questions, we can discuss with Professor over tea. Now, let's thanks again, Professor, for the nice talk.
Thank you.
And we will assemble again at 4 o'clock for the second talk.
Just coffee.